Dr. M. Subbaya is an assistant professor in mathematics in LN Government College, Poneri. He has specialized on statistics interdisciplinary. Being interested in active research program and mathematical or statistical modeling, he has knowledge in operating various softwares on statistical tools and on technical computing. Having 16 years of teaching experience, he has published papers in 8 national and international journals, and has also presented papers in 10 national and international conferences.
Welcome to UGC lecture series on mathematical sciences. So, the point of discussion for this session will be statistical inference. In that, we are trying to identify two methods for point estimation, namely MLE, that is maximum likelihood estimator, and another one is MOM or method of moments. So, first let us quickly review why should we have these kind of estimation procedures. The objective of this session would be mainly on these two, followed by few examples, but quick review about this parameter estimation would be helpful for the purpose of learning about these procedures MLE and MOM. So, basically this inference will be based on, or it is the aim of this inferential theory is to estimate few parameters. So, the idea is to understand two terminologies. What is the meaning of a parameter of interest, and sometime we may call as variable. So, we have a simple mechanism of this notation f of x given theta. So, of that the statistical inferential problem is primarily interested to understand something about this theta. So, what is this theta and what is this x? So, x may be understood as a mathematical expression for an event which is of having uncertainty. So, that a probabilistic model would be apt for understanding how that particular function would behave. So, this is something for the behavior of any event which is having uncertainty. So, probabilistic modeling is quite appropriate, whereas those functional form will have further more parameters or further more unknowns which may not be revealed in the first observation. We have to get, or we have to estimate the value of those symbols which we mentioned as theta here through a sample which can be drawn from the population under study. So, the problem is to estimate the unknown parameter theta from the given observation. So, we have a very big population under study and we are not able to derive entire information available in the population. Therefore, we are going for a sample. From the available information in the sample, we are trying to estimate the quantity of interest, what we call it as parameter, in different manners. So, one such procedure is point estimator. Let me give a simple example based on a fundamental distribution for count model, which is Poisson distribution. So, there are two terms here we would like to emphasize. One is about rare event, or sometime we may have a simple definition called count data. So, rare events are very much interest because the occurrence are very much probabilistic, very much undetermined. At the same time, we may not know what is the pattern of occurrence even. For example, number of calls received in a phone or mobile, whatever may be, or sometime number of accidents occurred in a particular road or a junction. So, it might happen at any point of time and quantum also. So, there are a lot of uncertainty involved in such events where we call it as rare event. So, in medical examples, break of any epidemic and the result of those kind of epidemic disease. So, these are all sometimes called as rare event, because the occurrence are purely based on the incident of occurrence, and the quantum is also very much unpredictable, in the sense whether it occurs in 1, 2, 3 or in large number also. So, therefore, the rare events are illustrated by that examples, or generally we call it as count data, which may take from 0, that means nil occurrence, and 1, 2, 3 and so on so forth. Suppose I take some n independent and identical distribution from a Poisson, and I am considering generally n samples generally, then I will be having one parameter of interest theta, and I model for y as summation of x I, then the likelihood of theta given y will become this formula. So, there is a new word we try to coin here, likelihood of the parameter when the data is being observed. That means, we have collected already this x 1, x 2 etcetera. Subsequently, I will show you what could be the real meaning for this x 1, x 2 and so on so forth. Time being, we try to understand that these are all some symbols where the first outcome, second outcome and so on, and it looks like a Poisson distribution in a mathematical structure where theta is unknown, and through the mathematical relation of Poisson distribution called additive property, we have y follows Poisson distribution with parameter n theta. So, n times theta. Therefore, this is a PDF of Poisson distribution, but here we use a word called likelihood, and the symbol also little reversed, in the sense earlier we started f of x given theta, understanding that we know theta, what would be the form of the data form, that is f of x given theta. Now, we are trying to do it the other way around. So, I have some sample, from the sample what could be the maximum possible, I mean the likelihood of this unknown quantity, what we call it as parameter would be. Therefore, the mathematical structure of Poisson distribution does not change, but the orientation of the study is entirely in a different perspective. That means, from the collected data, from the collected information, what would be the most probable or the chances for theta. That is why the word is not a function, we say that it is likelihood. Therefore, our aim, our objective is to estimate this estimate the parameter theta in this particular example. Generally also we follow the same symbol pattern. Further, I continue, how do I get this kind of estimator? So, one possibility would be it is based on the sample, therefore, it is a function, any function for that matter, as a point estimator of theta. So, we have to find out a suitable function in terms of the sample values x 1, x 2 etcetera, to understand the value or the plausibility, in the sense the reasonable or appropriate values for theta, because as far as Poisson distribution is concerned, the parameter range, that is the space for the parameter theta is positive, strictly positive. So, we have to estimate the value, and within this framework, that is what I mean to say plausible value. More realistic or more numerical example I could spot out here for the same problem, a data set on the number of awards earned by students at one school, based on the problem is actually for different purpose, but I have given here because of this occurrence. So, it may be influenced by the number of awards, may be influenced by the program offered in the school, may be of different level 1, 2, 3 and so on, and their score in mathematics. Then finally, the problem here interest would be how many awards the student is likely to. This is a very big large data set available here, but for the purpose of this illustration I just picked up few data points, because you could find out that the number of awards are likely start from 0, that means no award, even it goes to 6, sometime 4, sometime 2, sometime 3 or anything for that matter. So, this is what I told you, we do not know how many awards the students could score, though we are able to calculate the longevity of that particular student stayed in the school, and number of competitions or the tests are being conducted and so on and so forth. We can fine tune what could be the maximum award a student can get, but generally speaking, broadly speaking, the number of awards would be anywhere starting from 0, nil award, 1 award, towards 3, 4 and so on so forth. So, to mean to that we just try to observe this likelihood can be modeled as a Poisson distribution. Therefore, the real time or the rare events can be modeled with the help of Poisson distribution. That is the purpose for such illustrations. With the numerical example we observed, I just extended two more situation in which the number of certain cases can may be the variable of interest. Say for example, this is a very interesting and long term studied data set, Prussian horse kick data, which indicates the number of deaths by horse kick from the war period in 14 army corps. So, the people are interested in understanding this. So, these kind of events are coined as rare events. So, it may not be literally these rare versus frequent, but slightly different in the perspective. So, number of deaths here. In a similar way, another data which I try to say here is crab data, where the variable of interest is the number of satellites. Satellite is actually here the male crab. So, the problem of interest in this biological situation is how many male crab are available around a particular female crab. So, this is the problem of interest. It could be sometimes 0 or sometime 1, 2, 3 etc. So, if we observe the modeling aspect of the given problem, which are classified through the context of the problem as rare event, or generally a count data model, where we try to fix Poisson distribution would be most suitable data model. Mathematically speaking, there is a probability density function associated with this model. So, that is what in the very beginning of the session we modeled as f of x given theta. So, now we try to explore few examples by which this kind of symbol or what we observe so far as f of x given theta or theta given y, whatever may be the way in which we call, our idea is x or y refers data likelihood, data part. So, that would be modeled through a probabilistic distribution, that is lesson number 1. Second is invariably any distribution in its mathematical form has some 1 or 2 parameters, unknown quantities. Therefore, the problem is finding, listing out these 2 steps and then trying to estimate the unknown parameter. Therefore, so far we observe an illustrative example through which how a real time situation can be converted into a suitable model. It might be Poisson, it might be binomial, it might be gamma, it might be anything. Sometime even without this specification of a particular theoretical distribution, a functional form which may be categorized or formed as a PDF can also be used. Therefore, subsequent discussion will be focused on few numerical examples focusing on 2 methods for estimating the parameter. Initially, I would concentrate on single parameter, only one parameter involved in the given likelihood. So, let me list here that I have a likelihood. So, sometime it may be written as L of theta given x. So, that is the observation number 1 so far we have. Then I want to estimate theta. In symbol generally this is referred as theta hat. Third observation which we have not done so far is, instead of looking at L of theta given x, we may be sometime interested in small l, which is natural logarithm of the likelihood function. The reason being, invariably these are all product form. So, natural logarithm or logarithm would make the process much more simpler in additive form and for the subsequent procedures. Therefore, we may prefer invariably this logarithmic format. So, with this understanding, with this requirement, we are moving to a simple example. I may select even from the Poisson. So, I will select what we have discussed with so far, Poisson model. So, I have a random sample, say for example, I have n samples with me and we are interested in y equal to summation of x I. So, what we started earlier, same thing I mentioned with y. So, if x I is random sample collected from a Poisson family, then they are all independent and we have Poisson of theta. So, that implies y will follow Poisson of n theta. So, if I model with y, so L of theta given y, we have e power minus n theta raised to the power y by y factorial, where y equal to 0, 1, 2 etc. and 0 elsewhere. So, this is what we have mentioned already. So, our job is to calculate, but so I have first point, second point I have to do, for that I will get the help from this particular part. So, you could easily find out the logarithm will be make this expression much more easy to handle. One more aspect is what would be the functional importance. Here the importance is theta, therefore, any process would invariably make this y factorial or related to the data y as constant for that particular operation, because we are mostly interested on theta and assume that this y is known to us. Therefore, here the y factorial is mere a number and unknown quantity is going to be theta. Our job is to find out theta hat. So, this is a symbol throughout the discussion we will follow for indicating the estimated value for theta, the unknown parameter. So, now I will explain the procedure for MLE. So, we will start with the procedure for MLE. There are two procedures today. One is maximum likelihood estimators. So, it can be any kind of estimator based on this procedure. So, what we try to do, we will take a general case L of theta given x and then differentiate with respect to theta equate to 0 and find the solve for theta. So, this is a simple optimization problem, that is all. So, how this would be effectively applied for Poisson distribution. So, I have here. So, only one thing is we have made it from the log. So, I will go with small n ln of theta given x. So, that is going to be logarithm of e power minus n theta exponential of n theta power y by y factorial. So, using log rule, we have log of exponential of minus n theta plus log of n theta power y plus log of y factorial. So, it is minus n theta because these two are inverse function, and applying the logarithmic rule we have y times log of n theta, and this for time being I can make it as a constant because our interest is to look at with the theta, and here also you are going to differentiate with respect to theta. There is no term involved with the theta here. So, time being I just simply write it as C. So, the idea is finding out the maximum value based on L, capital L as its original form or the transformed log, both are same. Therefore, I am using that property. I just calculate small l equal to dou L by dou theta, which is going to be 0. I am going to equate, that will be minus n. So, this will be differentiating with respect to theta plus y times log of n theta is 1 by n theta into differentiation of n theta with respect to theta and equate to 0. So, that is going to be minus n plus y by theta equal to 0 or y by theta equal to n. I am solving for theta. Finally, I am getting theta equal to y by n. So, this is your likelihood, and here we are differentiating with respect to theta and equating to 0, and finally we solve for that. This term is actually referred to theta hat as y by n. Therefore, we solve it for theta to get this particular part, but y is already in our notation summation of x I by n. So, what we observe here is for a Poisson model, if you have collected n samples, the estimator for theta would be sample mean. So, once again we observe theta hat is sigma x I by I, sigma x I by n, which is going to be x bar. Therefore, this is a simple illustration or simple example through which we can understand that we could estimate the parameter theta by the given sample values. So, as n goes larger and larger, this estimated value is expected to be better. So, what is the meaning of that better and quality may not be the scope of this particular discussion. Still, we may have a question whether this theta cat could be or theta hat could be more reliable. It depends on many conditions. Still, this session is particularly about the first method, namely MLE, where these 4 steps are to be followed. Only the convention we follow is, instead of L, capital L and its original form, we may be interested in looking at log form and go for that, and because of the simplicity here involved in the calculations. Then I may take another case for theta hat through the second method called MOM. Same problem, question is to estimate theta, but the method is now MOM. So, MOM is actually through equating moments, maybe central or non-central moments, from 2 ways. One is from the population model itself, another one is from the sample. So, conveniently, for example, for the first moment, for example, if I have moment number 1, here it is the sample mean, notational sake, here it is expectation of x. If I calculate expectation of x and equate to x bar, and here it is involved with the population parameters. So, here it is involved with the E of x, and here it is involved with the sample values. Equate and then solve for theta. So, obviously, if we have only one parameter, I may require to have only one equation connecting moments of sample mean, sample and population. Thereby, I am able to solve it. So, if my parameter set has 2, then naturally I will go to 2 moments, then solve for 2 equations and etc. This may look very simple method. In fact, it is very simple, but sometime the property may not be so optimum. So, let us try to work out this particular part here. If you take once again our Poisson case, I just want to float one more time that case, because it is easy to understand. So, we have a Poisson distribution, and then if I take the population moment E of x, it is simply theta and sample bar is x bar. If the responsibility is to equate them, theta hat equal to x bar. This is what earlier we observed. Therefore, it is a very simple example to visualize what could be my sample mean and population mean. So, first moment I have calculated. For Poisson distribution, we know that it is theta. Sample mean is referred by x bar generally, and second step is simple, you just equate directly, we are able to get, but not all the time we have such comfort. Let us have an example for such a distinct case or where we have to discuss. I will take some other example. This case f of x equal to theta into x power theta minus 1, where this x is given as 0 to 1. Though now it is not very much important, let us take this one. So, in our notational form, based on n sample, my likelihood will be product of this theta x I to the power theta minus 1. So, I have collected n samples. I follow our language introduced in the session L, but we are going to have small l, which is the logarithmic transformation of this particular part. Therefore, I will be taking L of theta given x, that is going to be. So, product will become addition, theta will be multiplied for n times, therefore, logarithm of theta power n plus theta minus 1 into summation of log of x I. So, this theta is multiplied n times, therefore, there will be theta power n. Ultimately, n into log theta plus theta minus 1 times summation of log x I. Suppose I differentiate this dou L by dou theta equal to 0 and then I will equate to 0, then it implies n into 1 by theta plus summation of log x I equal to 0. That further implies I have to solve this theta. So, we have n by theta equal to this one, therefore, I get theta equal to minus of summation of log x I divided by n. So, I call it as theta hat now. So, what we have done, step 1 likelihood, log transformation, differentiation and 0, then we get theta hat. Therefore, we have followed strictly the principle of MLE, maximum likelihood estimator. I have used the procedure for finding MLE using these 3 steps. Let us now work out MOM also. So, if I try to do MOM for this particular case, what will happen if I take expectation of x? So, expectation of x is integral 0 to 1 because the x is varying from 0 to 1 and x into theta x power theta minus 1 dx. So, theta times integral 0 to 1 x raised to the power theta dx or else theta times x power theta plus 1 by theta plus 1 from the limit 0 to 1 and applying the limit properly, we have theta by theta plus 1. So, expectation of x is obtained like this. So, in MOM what we observed is we have to equate population mean with sample mean if I have only one parameter. For the given distribution of the form theta into x power theta minus 1 for the method of moments, I have calculated population mean. I have on the other hand sample mean. So, what I have is sample mean x bar, the usual symbol. Second step for MOM is equate. So, what should be equated? Theta by theta plus 1 equal to x bar. So, I just cross multiply it, theta plus 1 times x bar. So, theta minus theta times x bar equal to x bar. If I take theta outside, you will have 1 minus x bar. So, theta hat finally is x bar by 1 minus x bar. So, for quicker comparison, I just recall the answer of MLE for here theta hat is equivalently with minus of summation of log x I by n. So, this is an answer from MLE, this is an answer by MOM. So, the first example which illustrates that MLE and MOM can be equal, but the second example, a simple example of the form, clearly makes a difference between the procedures. Maximum likelihood estimator might yield a different answer, whereas MOM, method of moments, might yield a different answer. This is x bar. So, the procedural difference what we have here is illustrated, as well as the answers may or may not be the same. Therefore, it is in the initial stage of our today discussion says we are having a function of x 1, x 2, etc., x n, which may be an estimator. So, in the first example, in the case of Poisson, both method yields the same estimator as the sample mean, whereas the second example shows that MLE and MOM yield different estimators, which may be a function of x bar, but anyway it is a function of x 1, x 2, etc., x n. For that means given are the sampled value from 1 to n may be anything. So, that issues are not being discussed here. Therefore, this discussion completely focuses on the meaning for point estimator and two type of estimation method for estimation has been discussed. One is MLE, another one is MOM, and examples illustrating how they could be a function of x 1, x 2, etc., x n may or may not be one and the same, through which we can understand that there are other procedures even to get the different type of estimators, which we call it as point estimation. So, these are all few examples through which we can give an example for normal, and then here it is the same distribution, but with MLE form, and a gamma with only one parameter is tried to give. So, the problems are collected from the given text for the easier references and further practice. Thank you for joining this session.